All right, we're going to go ahead and get started. Chapter 5 is going to take a little while. I think if you look in the modules, I have it up for you so you can see how long it's going to take. But I know that there is one day, it may be Wednesday or Thursday this week, that it looks like you have a lot of homework, but half of it's like multiple choice. So don't freak out when you get there. And then the next day, it's like 4 questions. So it kind of balances itself out. And if you guys need to take a little extra time, that's okay. I'll dictate what that is. Okay. So when we get there, we'll worry about that. But for right now, we're just going to start with this and we're only going to do about 3 pages and then we're going to be done like always. So just going over this activity, we don't have to do it, but I want to give you an idea of what it was. As a special promotion to its 20-ounce bottles of soda, a soft drink company printed a message on the inside of each bottle cap. Some of the caps said, "Please try again," while others said, "You're a winner." The company advertised the promotion with the slogan, "One in six wins a prize." The prize is a free 20-ounce bottle of soda, which comes out of the store owner's profits. 7 friends each buy one 20-ounce bottle at a local convenience store. The store clerk is surprised when 3 of them win a prize. The store owner is concerned about losing money from giving away too many free sodas. She wonders if this group of friends is just lucky or if the company's 1 in 6 claim is inaccurate. In this activity, you and your classmates will perform a simulation to help answer this question. So this is a simulation we would perform, but in the situation that we're in, we're not going to do that. So for now, let's assume that the company's telling the truth and that every 20-ounce bottle of soda it fills has a 1 in 6 chance of getting a cap that says you're a winner. We can model this, sorry, the status of an individual bottle with a six-sided die. Let 1 through 5 represent "Please try again," and 6 represent "You're a winner." So you're going to roll your dice 7 times to imitate the process of the 7 friends trying to buy their soda. How many of them won a prize? So you just keep flipping. And this is, everybody's supposed to be doing it, so everybody would get different results. We would do a dot plot and then see if we can get at least 40 repetitions and then decide what percent of the time did the friends come away with 3 or more prizes just by chance. Does it seem plausible that the company is telling the truth, but the 7 friends just got lucky? So is it plausible? Yes, it is. Remember, 1 in 6 is just an overall general thing. What you'll learn is with probability, it becomes a 1 in 6 chance over a long period of time. So as we do this, doing 40 repetitions, we may not see a big chance of getting the 3 winners. But if we did it multiple times, like 5,000 times, it would get closer to that 1 in 6 chance. Okay. So again, probability is not what happens right now. Probability is what happens after many times. And that's what you need to basically get out of this unit. So simulation, which is what they just did with the dice, is a powerful method for modeling chance behavior. Probability calculations are the basis for inference. So that just leads you into the chapter and talking about probability. So now we're going to talk about randomness, probability, and simulation. And we're going to save simulation for tomorrow. So just those 2 beginning things are what we're going to do. So once we get to the word simulation or the heading simulation, we're done. All right, just to throw that out there. So in football, a coin toss helps determine which team gets the ball first. Why do the rules of football require a coin toss? Because tossing a coin seems a fair way to decide. That's one reason why statisticians recommend random sample and randomized experiments. They avoid bias by letting chance decide who gets selected or who receives which treatment. A big fact emerges when we watch coin tosses or the results of random sampling and random assignment. If we watch it closely, we can see that chance behavior is unpredictable, in the short run, that has a regular and predictable pattern in the long run. This remarkable fact is the basis for the idea of probability. All right. So I'm gonna hold off a minute. Let me find this applet for you guys. I always forget what it is. No, I got it. Zoomers, hang out for a minute. Sorry, y'all. Okay. So I'm going to show you this applet, and it's in your book. You guys, it has the website and everything within this. So what it does, you guys see, okay, yeah. It says, if you toss a fair coin, what's the chance that it shows heads? It's 1/2 or 50%, right? In this activity, you'll use the probability applet to investigate what probability really means. So this is the probability applet that it's talking about. So it says, if you toss a fair coin 10 times, how many heads will you get? So here's your probability of heads is 50%, but we're going to drop our tosses to 10, and we're going to toss it, and it's going to show you what happens, okay? What was our actual probability? Was it 50%? No, it was the heads is blue, heads 20 and tails were 80. Did everybody see that? But it said it was 50, right? So when we toss a coin, it's supposed to be 50-50. But that's what it's talking about. In the short run, it's super unpredictable. So we're going to reset this and try it again and see what happens this time. This time we got heads was 40, but tails was 60. So that contradicts what we just found out, right? Okay. So then it says, what if you toss the coin 100 times? So now we're going to change this to 100. Now we're going to toss it. And it shows it shows everything, but it's not important. What's important is the end. Look at that graph. What's happening on the graph? Y'all have to talk to me.
It evens out.
Yeah, it kind of levels out, right? So in the very beginning, it jumps around. It goes from being a really high probability to lower, and then kind of like super spikes. And then eventually on the end, it levels out. So is the proportion of heads exactly equal to 50%? Yes or no? No, but is it close?
Yeah.
Yeah, so that's number 2. Then it says keep tossing without hitting reset. So I'm just going to keep tossing and just watch what happens. So now we've tossed it 200 times, or when it finishes, that'll be 200 times. What are we at now?
51%.
Yeah, so really close, right? Hey, I'm zooming. How you doing?
Good.
What you need?
It's on the door.
It don't have to be on the door.
Yeah,
No, it doesn't.
I'm interrupting your whole thing.
It's okay.
Who are you zooming with?
Everybody in my class.
Everybody? Hey, everybody.
See,
They're not answering.
that's
Hello.
there. That's how
What'd
they
she
do me.
say?
I don't have no idea.
What did she say about assignments for tomorrow?
We don't have any.
Hi.
Surprise. Can't talk about that in here though. They'll tell on me.
Why are you so loud?
That's right. I'm gonna go interrupt ladies now.
She's having a Zoom too, just
Is she
FYI.
close?
Yes. We teach. So as it keeps going, you can see that it'll get closer and closer to 50-50. So it keeps leveling out even more. Sorry, y'all, that we were interrupted. But every time it's just going to be close to 50. It's not going to be exact. The more times you do it, the more repetitions that you have, the closer it's going to get. So predict what will happen if you change the probability of heads to 0.3, which would be an unfair coin. And we're just going to drop it to 0.3, and I don't need you to predict. We're just going to check it out. 0.3. Let's take our tosses back to 25. Oh, let me reset. So you can see again, as we toss, like it started being sporadic, and then it's going to keep leveling it out. So the more that we do this, it'll keep leveling out. But where is it going to level out to this time?
0.3.
0.3, the probability of getting heads. So heads should sneak closer to 0.3 every single time. And the more I do it, the closer it's going to get. All right. If you toss a coin, it can land heads or tails. If you toss a thumbtack, it can land with the point sticking up or the point down. Does that mean that the probability of a toss thumbtack landing point up is 50%? And how could you find out? What do you think?
You just look at it and see the shape isn't right.
Y'all good with that? Yeah, it's not going to be fair at all. So how could you find it out? You could flip that tack 50,000 times if you want to and see what probability you get. All right. So I'm going to stop this share and go back to our notes. I just wanted to show you that probability applet. I don't want to get back to that. I want to go to this. All right. So we might suspect that a coin has a probability of 0.5 of coming up heads just because the coin has two sides. But we can't be sure. In fact, spinning a penny on a flat surface rather than tossing a coin gives heads a probability of about 0.45 rather than 0.5. What about thumbtacks? They also have two ways to land, point up or point down. But the chance that a toss thumbtack point lands point up isn't 0.5. How do we know? From tossing a thumbtack over and over again. Probability describes what happens in very many trials. That's what you need to know. And I told you guys that's the big thing that you need to get out of this. And we must actually observe many tosses of a coin or thumbtack to pin down a probability. Okay, so again, it's not that the coin has two sides, it's that over time, it's shown that it has a 50% chance every time you toss it. So example, tossing coins, short run and long run behavior. When you toss a coin, there are only two possible outcomes, heads or tails. The first figure below shows the result of tossing a coin 20 times. For each number of tosses from 1 to 20, we have plotted the proportion of those tosses that give a head. You can see that the proportion of heads starts at 1. That means the first toss was heads, so you had 100% heads. Then it falls to 0.5 because you got a tails when the second toss gives a tail. Then rises to 0.67. Again, 2 out of 3. And then falls to 0.5 and 0.4 as we get 2 more trials. After that, the proportion of heads continues to fluctuate, but never exceeds 50% again. And again, that's the same thing the applet just showed you. It's not anything any different. So suppose we keep tossing the coin until we have made 500 tosses. The next figure shows the results. The proportion of tosses that produce heads is quite variable. At first, as we make more and more tosses, however, the proportion of heads should say gets close to 0.5 and stays there. So again, same thing, it fluctuates a lot and then it levels out, just like I told you on the applet. All right. The fact that the proportion of heads in many tosses eventually closes in on 0.5 is guaranteed by the law of large numbers. You need to know the law of large numbers. Okay, make sure you know the law of large numbers. This important results say that if we observe, sorry, stumbling all over my words today, more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches a single value. We call this value the probability. The previous example confirms that the probability of getting ahead when we toss a fair coin is 0.5. Probability 0.5 means, you need to know this is the definition of probability. So if they ask you what does 0.5 probability mean, you need to be able to say this. Occurs half the time in a very large number of trials. So again, if they ask you to interpret probability, that is interpreting probability. All right. Probability of any outcome of a chance process is a number between 0 and 1. You need to know that. Why is it between 0 and 1? 0 chance to 100%. So 0 to 100. That describes the proportion of times the outcome would occur in a very long series of repetitions. Outcomes that never occur have a probability of what? Never occur. 0. An outcome that happens on every repetition has a probability of what? 1. An outcome that happens half the time in a very long series of trials has a probability of 0.5. Of course, we can never observe a probability exactly. We could always continue tossing the coin. For example, the mathematics of probability is based on imagining what would happen in an indefinitely I think I spelled that, yeah, I did. T-E-O-I, indefinitely long series of trials, sorry. Probability gives us a language to describe the long-term regularity of random behavior. The outcome of a coin toss and the gender of the next baby born at a local hospital are both random. So is the result of a random sample or a random assignment? Even life insurance, for example, is based on the fact that the deaths occur at random among many individuals. All right, so, wow. All right. Check this out on page 292. Just make sure you read over it. It basically is just talking about how, like, people have to pay extra for cancer stuff. Like, when we do our insurance sign up, there is a cancer policy that we can buy. So, that, like, if you're prone to it, like if it's in your family or something like that, you can go ahead and buy it. You may not ever use it, but you can buy it just in case. If you are a smoker, your premiums go up, things like that, things that are high risk or that you make, like if you're overweight, your premiums go up. So, and they just use that as chance process. What's likely is if you're overweight, you're going to have a heart attack and they're going to have to pay money out. Okay. So they're going to get more money from you because they're going to have to be dishing more money out for you. All right. So that's basically what it talks about in there. So we often encounter the unpredictable side of randomness in our everyday life. But we rarely see enough repetitions of the same chance process to observe the long run regularity that probability describes. Life insurance companies, casinos, and others who make important decisions based on probability rely on the long run probability of random behavior. So one more page front and back and like one little paragraph. Okay. According to the Book of Odds website, the probability that a randomly selected U.S. adult usually eats breakfast is 0.61. Explain what probability 0.61 means in this setting. That's interpreting probability. So I'm going to go ahead and show you what this one is so that you have it down and you can make sure that you do it, especially in your homework tonight, okay? So if you asked a large number of U.S. adults, you could say many, many adults, and we'll talk about that soon. I know that sounds so trivial and babyish, but that's really true. If you ask a large number of U.S. adults if they eat breakfast, we have to say about because it's never exact. Remember, probability is never exact. About 61% of them would say yes. Okay, and again, because it says the probability that a randomly selected U.S. adult usually eats breakfast. Okay, you have to ask them because you don't know. You would have to observe it. Why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them usually eat breakfast? Okay, so just like with the coin toss, when I tossed it the first time, what did we get? Like 60-40, something like, oh, we got 80-20. Then I reset it, and the second time I tossed, it got like 60-40. So what you did was you took two different samples, okay? So we just got done talking about random samples. So you took a sample of 10 coins, we tossed it, and then we put it to the side. Then we took another sample of 10. Those two samples did not give us the same results, okay? So why doesn't this probability say that if 100 U.S. adults are chosen at random, exactly 61 of them eat breakfast? Because if we get a different sample, All right. We could have a higher or lower percentage. And again, so that's the same concept. Like if you put all the names in the hat and you draw those names out, you draw 10 names out. When you put them back in the hat and you draw 10 more out, are you likely to get the same sample? No, chances are you're not going to get the same sample. Could you? You could. It'd be really, really lucky that you did. But that's all it's saying is I could pick these 61 or whatever, these 100 right here, and then I'll pick the other 100, but they're not going to have the same result. All right. So just know these two right here. Okay. Why wouldn't you get the same probability? Because you could have a different sample. What is the definition of probability? After you ask a large number or after many, many times, about 61% would be whatever the favorable outcome would be. All right. Probability is a measure of how likely an outcome is to occur. Match one of the probabilities that follow with each statement. Be prepared to defend your answer. The outcome is impossible. It will never happen. What's your probability?
0.
0. So we use that one. The outcome is certain. It will occur every trial.
1.
1. This outcome is very unlikely, but it will occur once in a while in a long sequence of trials. It is
0.01.
unlikely. Yes, very unlikely, but it could occur. This outcome will occur more often than not.
0.6.
Good. Any questions with any of those? What would 0.99 be?
Almost always.
Almost always. Yep. So not exactly always, just almost always. What about 0.3? Something we could do with 0.3?
Been some of the time, like every few.
Yeah. So the outcome will occur more often than not. Maybe the opposite way will not occur. All right, we're gonna be fine. Flip it over.
Hey, Miss Jones.
But
Haley got kicked out of the Zoom. Is she?
I'll put her back in.
Okay, you did. I just saw her message.
It's okay. All right.
Rachel, that was a while ago.
Well, okay, I'm not on my phone through the whole class.
No, I'm back on.
Hey, we're recording, so I need you guys to stop. Thank you. The idea of probability seems straightforward. It answers the question, what would happen if we did this many times? In fact, both the behavior of random phenomena and the idea of probability are a bit subtle. So then we can investigate randomness. This is just an activity, so we can read over it real fast and then we'll move on. Pretend that you're flipping a fair coin without actually flipping a coin. Imagine the first toss, write down the result you see in your mind, heads or tails. Imagine a second flip, write down the result. Keep doing this until you've recorded 50 imaginary flips. Write your results in groups of 5 to make it easier to read like this. Heads, tails, head, tails, head, tail, tail, head, head, tail, etc. A run is a repetition of the same result. In this example, in step 3, there is a run of 2 tails followed by a run of 2 heads in the first coin flips. So right here, a run of 2 and a run of 2. Read through your 50 imagined coin flips and find the longest run. So your teacher will draw. We're not doing that. You can use Table D technology or coin to generate a similar list of 50 coin flips. So like you could do 1 and 2. 1 would be heads, 2 would be tails. So you could do that instead of doing it in your head. You're going to find the longest run and you're going to plot that. And then we compare the distributions. But again, we're not going to do that because we don't have everybody in class. So the idea of probability is that randomness is predictable in the long run. Unfortunately, our intuition about randomness tries to tell us that random phenomena should also be predictable in the short run. When they aren't, we look for some explanation other than chance variation. All right, so runs and coin tossing. They're just going to go over exactly what they are supposed to do in that activity. Toss a coin 6 times and records heads or tails on each toss. Which of the following outcomes is more probable? So which one do you think is more likely to happen, the first one or the second one? The first one. So almost everybody says that the first one is more probable because the second one does not look random. In fact, both are equally likely. That heads and tails are equally probable says only that about half of a very long sequence of tosses will be heads. It doesn't say that heads and tails must come close to alternating in the short run. The coin has no memory. It doesn't know what past outcomes were, and it can't try to create a balanced sequence. So what it's saying is this shows 50% heads, and this shows 50% heads. So they're both equally likely, but one just looks weird when you look at it. So one looks like it's not going to happen. So the outcome, TTT, HHH, and tossing 6 coins looks unusual because of the runs of 3 straight tails and 3 straight heads. Runs seem not random to our intuition, but are quite common. Here's a more striking example than tossing coins. So like even when you're taking like your multiple choice test and you start getting like A, and you start freaking out because you know it just can't be 3 A's in a row. It can be, don't freak out. That's what they're saying. So example, the shooter seems hot on page 294. You guys can read over that. So basically what it says is the shooters, I think this one is shooting free throws and he's making them like the whole time. So is it chance variation or skill? We don't really know. Read over that, check it out. Just remember that coins and dice have no memories. A coin doesn't know that the first 6 outcomes were tails, and it can't try to get ahead on the next toss even if things to even things out. So if you flip and you keep getting tails, the coin is not going to be like, hey, I flipped to tails every time. I'm gonna flip to heads this time. That's all that's saying. Okay. Of course, things do even out in the long run. That's the law of large numbers. In action, after 10,000 tosses, the results of the first 6 tosses don't even matter. They are overwhelmed by the results of the next 9,994 tosses. And then it says, example, are we due for a boy? Don't fall for the law of averages. So the law of averages, if, so for example, there's a girl that I went to high school with, and she has had 3 babies, and she is pregnant with her 4th one. All 3 babies have been a girl. What's the next one going to be? What's it going to be? Do you know? It's equally likely to be a girl or a boy, right? But just because we've had 3 girls, does that make it more likely that this one is going to be a boy or more likely that it's going to be a girl? And that's all that's saying. Don't fall for the law of averages. It says, you know, hey, I've had 3 girls. Chances are now I'm going to get a boy. That's not always the case. So you still have a 50-50 chance of getting both regardless of what happened before. Does that make sense? So that's all it's saying. So the difference in don't, like it's saying don't fall for the law of averages. Don't just assume that the next one's going to be a boy or whatever. So that's exactly what that are we due for a baby boy is. And that's it. That's all we're doing today. And then we're going to go to simulation. So I'm going to stop the share.